Hello, it's 8:30 Tuesday evening, so after my first attempt to record today's lecture failed, I'm back here at Southern Hall, 302, to an empty room to try giving this lecture and recording it again. And now that the laptop is plugged in, hopefully I won't have the same issue as last time, but we'll find out. And yes, this does feel weird for me doing this, but it's not the first time. All right, so what I'm going to cover, again, is section 8.3, and that is fixed point iteration. Okay, this is section 8.3 in the notes. So the idea behind fixed point iteration, very different from bisection, is that we're going to solve the equation that we have been talking about, f of x equals 0, by rewriting the equation in this form. X is equal to g of x. And there are many different ways to do that, and we'll talk about that, how that can be done as we go. But the idea is, once you have it written in that form, then you have a very simple algorithm for solving it. To use what is called fixed point iteration, also known as successive substitution. And you'll see why it has that name in just a little bit. So I'm going to write the algorithm right here. It's very short. Actually simpler than bisection. So the first thing you do is, just like bisection, you're going to generate a sequence of iterates. You start with an initial guess, x naught. So that is your initial guess as to the solution. And then you're going to generate x1, x2, x3, and so on. That will hopefully converge to a root x star. So what you do is quite a simple process. So just have a loop. It'll keep going as long as you need it. And to get each new iterate, xk plus 1, all you do is substitute your previous iterate, xk, into your function g. And what's going to happen is, if the iterates xk actually converge to a limit, then this equation x equals g of x will be satisfied, because these will converge to something that is equal. And then all we have to do is check for convergence. So we can just check, for instance, if the difference between two consecutive iterates is less than some error tolerance, like maybe 10 to the minus 8, whatever it is you choose. And if that's the case, then your root x star will be declared to be xk plus 1. And that's it. That's the whole algorithm in a nutshell. So if the iteration converges, then it will produce a root x star that satisfies x equals g of x, which for properly chosen g will be equivalent to the original equation you're trying to solve, f of x equals 0. But we have questions to answer about this iteration. So those questions which we'll tackle are, first of all, when does this iteration converge? And the second question is, if it converges, how rapidly does this iteration converge? So before we can feel comfortable using this method as an alternative to bisection or any other method, we need to know what's going on. And to illustrate some of the issues that come up with developing a convergent iteration, we'll take a look at an example. example, we want to solve the equation x plus natural log of x equals 0. So the question becomes how to choose g of x, because this function x plus natural log of x, this is our f of x that we want to find a 0 of, but we want to rewrite this as x equals g of x. What you can always do is the following: g of x equals x minus some function phi of x, which preferably should be non-zero, times f of x. And to see why this makes sense, suppose f of x equals 0 at a certain point. This entire term goes away, and you're left with g of x equals x. Similarly, if g of x equals x, then the only way that's possible is for this whole term to be 0, therefore f of x has to equal 0. So under these circumstances, this kind of equation, however we choose a non-zero phi, is equivalent to, actually I shouldn't write it like that. What we have is f of x equals 0 if and only if x equals g of x. So the idea is this makes the two equations equivalent. So here's what we can do. In this example, and we're free to choose phi of x however we like, but we'll make a simple choice. Let's let phi of x equal 1. So can't get a simpler non-zero function than that. So that means that g of x is equal to x minus f of x, which is x plus natural log of x. And the x's will cancel, and you're left with minus natural log of x. Now we're going to solve x equals minus natural log of x. Now, of course, we could see that this equation is equivalent to our original one by just going back up here and moving natural log of x to the other side. But it doesn't always work out as simply as that. It all depends on what your function f of x is. So that's why I want to show you this general form of g of x, because if you don't know what else to do, if there's no obvious way to rearrange the equation, then this is something you can always try. But even when we do have a simple way to rearrange the equation like we do here, that doesn't necessarily mean that the g of x you wind up with, is, for instance, in this case, minus natural log of x, doesn't mean it's going to work. So let's try it out. So for one thing, if we look at the graph, you can see that by the intermediate value theorem, our original function, x plus natural log of x, has a unique root. And it lies in the interval between 0.5 and 0.6. You can just plug both those points into x plus ln of x, find that one of the values is positive, and the other one is negative. So you know there's a root in that interval. So that gives us an idea of how to choose an initial guess. So let's go ahead and do that. Our initial guess, let's just choose the midpoint of an interval. So x naught equals 0.55. And now we'll compute a few iterates and see what happens. So x1 is going to be g of x naught. So that's going to be minus natural log of x naught. And I've gone ahead and done that in my notes. So what we get is, I'll just use 3 decimal places, 0.598. Okay, so we're still within the interval 0.5 to 0.6. Let's go again. x2 is minus natural log of x1. So we just keep substituting into minus natural log of x, and we get 0.514. Okay, and then x3 is minus natural log of x2, and we get 0.665. Now that's quite discouraging because we got bounced outside the interval 0.5 to 0.6. So it seems like we're diverging. And in fact, I don't have this in my notes, but I'll go ahead and do one more. x4 is minus natural log of x3. So I'll just use my handy calculator here. And if I do 0.665 natural log of x and negate that, I get 0.408. So again, outside the interval and going back the other way. So the iterates seem to be bouncing around quite a bit, and there's no sign of convergence whatsoever. So what's happening here is the iteration fails to converge. So this is a bad choice of G. It seemed like the most obvious choice, but it shows why we need to be careful. So we need to take a closer look at what's going on here to figure out why this iteration failed to converge and what can we do about it. Actually, I shouldn't have erased that board because what I need to do now is I'm going to temporarily stop recording and make sure that this clip is actually saved. And if it fails on me again, I'm going to be very upset because then I have to write that board again and record all of this again. I have 12 minutes of footage. Okay, let's see what happens. Okay, much to my relief, that clip recorded successfully. So we're good to go. Okay, so why did g of x equal natural log of x fail? Let's see what happens to the error. So I'm going to let e sub k equal xk, our kth iterate, minus our exact solution x star. So this represents the error after k iterations. Okay. So let's look at the error after k plus 1 iterations. That is xk plus 1 minus x star. But xk plus 1 is, by the algorithm, g of xk. And x star is equal to g of x star. Because x star is a solution. And I should mention some terminology here. So x star is g of x star. And what we say is, it's not just a solution of this equation. We say that x star is a fixed point of g. So that's a general term that's used for this situation, where you plug the x value into a function, you get the same x value out. It's also called a stationary point or an equilibrium point. In my other class 605, we'd give this term like 4 or 5 names. It's ridiculous, but I'll just refer to it as a fixed point here. And this is where fixed point iteration gets its name. So now that I have this, I have a difference of g values, I can rewrite this as g prime at some unknown point, which I'll call ck, xk minus x star. And earlier today I asked the class, what theorem from Calculus 1 allows me to rewrite this difference in g values in this form using the derivative? Eventually what the class said was the mean value theorem. which you probably remember as being written this way. F of b minus f of a over b minus a is equal to f prime of c, where c is in the interval ab is an unknown point. Just as ck is actually between xk and x star. Now, even though this is how the theorem is normally presented, it's actually most useful written this way. If you don't have a b minus a down here, and you instead have it up here. Because often what you have is a difference of function values, same function at different x values, and you rewrite it in terms of a derivative times the difference of x values. That is an extremely valuable way to use the mean value theorem to rewrite expressions in a certain form to prove something. And that's exactly what has been done here. So better to remember it the way I have it now, with b minus a in the numerator on the right side, to see how to actually apply it. So back over here, what we have is a derivative times ek. So the error after k plus 1 iterations is equal to the error after k iterations times g prime at some unknown point in between. So what if this derivative is large in absolute value? For instance, if it's greater than 1 or less than minus 1. So greater than 1 in absolute value. That means the error is actually increasing from one iteration to the next. We want it to go to 0. So what we need is the absolute value of g prime to be less than 1, at least near the fixed point. But in this case, in our example, g is equal to minus natural log of x up here. What's the derivative of this? Well, the derivative is minus 1 over x. And our x values that we're considering are intervals between 0.5 and 0.6. You plug in anything from this interval into here, you're going to get something that is like near minus 2. So, sort of like between minus 2 and like minus 1.666 repeating. So, as a result, the derivative is greater than 1 in absolute value. The error is increasing from one iteration to the next. So that is why the iteration fails in this case. However, not all is lost, because the fact that we know that this is a problem suggests what can be done about it. So here's what we can do. Make use of inverse function, assuming the inverse exists. And if the fixed point is not a double root of f, then at least locally, the inverse of g will exist. Okay. All right. So here's what we can do in general. We take x equals g of x, and I apply g inverse of x to both sides. Well, the g inverse and g will cancel, and you're left with x. So what that means is x is equal to g of x if and only if x is equal to g inverse of x. So, if x equals g of x fails because its derivative is too large near a fixed point, we can switch to using the inverse, assuming we can actually rearrange the equation that way. And now, why should that work? Well, I brought up this differentiation rule before. In fact, I did it last week, I believe. That the derivative of the inverse function is 1 over g prime of g inverse of x. So what's happening is by taking a derivative of the inverse, we're taking a reciprocal of a derivative of g. So if a derivative of g is too big, then the derivative of g inverse will be sufficiently small. So let's see what happens in this case. So if I let y equal minus natural log of x. In order to find the inverse, I have to solve this equation for x. So I'll have ln x is equal to minus y. So x is equal to e to the minus y. So this is g inverse of y. Yeah, I know you're supposed to like switch the variables when you find inverse functions, and I don't actually believe in any of that for reasons I won't get into here. But the point is, we know what d inverse is. So the original function is minus natural log. So the inverse function is, so g inverse of x also would be e to the minus x. So whatever letter you have in here, this represents what the function is doing. So let's try fixed point iteration on the equation x is equal to e to the minus x. And x is still between 0.5 and 0.6. We're still working with the same interval, and we might as well work with the same initial guess, 0.55. So now we can just plug in iterates again and see what happens. So x1 is e to the minus x naught, and that turns out to be 0.577. Then x2 is e to the minus x1, and that is 0.562. And then x3 is e to the minus x2, and that's going to be 0.570. So at least all the iterates are clustering around and is behaving a whole lot better than before. We're staying in the interval at least. I'll do one more by calculator. So e to the minus x3. Okay, so minus exponential, and I get 0.565. It is bouncing around a little bit. Now, that's not something to be alarmed about just by itself, because it's going to be bouncing around less and less. The reason why it's oscillating around a solution is because the derivative of this g function, e to the minus x, is negative. The derivative of e to the minus x is minus e to the minus x. So the sign of the error is going to keep alternating between positive and negative. But because the derivative is now less than 1, then what happens in this case is the size of the error, magnitude or absolute value of the error is going to decrease. So this is behaving what you want to do. And if you're not sure, we can actually try this in the lab on Thursday. We can try several more iterations and see that it actually will converge to a solution. So if you have that iteration x equals g of x and you find that it's not going to work because the derivative is too big, and you can check that before you start, go ahead and try inverting the equation using g inverse, and that iteration actually will converge. Okay, so now that we have some idea of what can go wrong and how to fix it, let's step back a bit and do some more rigorous convergence analysis. We want to know, when does a solution, a fixed point, even exist? When is it unique? Under what circumstances? Here we have an idea, but we'd like to know more rigorously, have some guarantee, theoretically, when this is going to converge. Actually, now that I'm really into this, the fact that there's nobody in the room with me barely even registers anymore. So it doesn't feel as strange as it did at the start. Except giving this lecture twice is a pain, so hopefully I can get this over with. Okay. So let's do some more rigorous convergence analysis. Now, first let's tackle the question of existence. So for existence, we have what is called Brouwer's fixed point theorem. There are actually many fixed point theorems. There are many fixed point theorems. So just one of two that we'll need today, but there are several others beyond the scope of this course. So if function g is continuous, we're dealing with always continuous functions here on an interval AB, and this is an especially important point, g maps the interval AB into itself. Now, what I mean by that is, if x is in AB, then g of x is also in AB. So once you're inside the interval, you can't get out by plugging in a g. G of x is going to keep points that are already in the interval still in the interval. So if that happens, then g has a fixed point, x star, and that fixed point lies in the interval AB. It's not necessarily unique. There may be more than one, but we know that at least there is one. Now, why should this be the case? We can I can give you an idea about that visually. So here we have the line y equals x. So you want x equal to g of x, because remember, what I mean by fixed point is x star equals g of x star. So one way you can look at this is the graph of g of x has to intersect, so this function has to intersect this function, y equals x. So the graph has to intersect this line. So here's my interval from A to B, and I'll just map that same interval onto the y-axis. So the idea is I have to make sure that for any x I plug in here, that the corresponding y values are somewhere in here. They don't have to take up the whole interval, they just need to be contained within it. So for instance, so the graph might be behaving, I'll just draw the portion in AB, something like this. So the y values are at least contained within. So in this case, there happen to be two fixed points, and I guess you're kind of angling towards the third one there. But the point is, x values within AB, when mapped plugged into G, still give you something in AB. On the other hand, let's suppose that when I plug in x values from AB, the corresponding y values are somewhere way up here. So G does not map, so it maps AB to some whole other interval way up here along the y-axis. But there's no way that there's going to be an intersection of this graph of G with the line y equals x. It's impossible. So that's why we need this function g to map the interval AB into itself. So if you can find some interval, AB, any interval where that happens, you know that a fixed point exists. Okay. So that's the start. But now we need to impose additional conditions on G in order to ensure that a solution is unique or that fixed point iteration will actually converge. So now we have a question of uniqueness and also convergence of fixed point iteration. Okay, so there are actually two conditions, two separate conditions, so we don't need one of the two to apply in order to have in order to have a unique solution and also a convergence. So first, in both cases that I'm going to describe,
I have way too many pages here.
now before I get into this, we're going to make the same assumptions as in the Brouwer fixed point theorem. G is continuous on AB, and G maps the interval AB into itself. Excuse me, love allergies. Okay. So one possible criterion that gives us uniqueness is called the contraction mapping theorem. All right, so if Brouwer's fixed point theorem is already satisfied, what the contraction mapping theorem says is if g of x minus g of y is less than or equal to some constant L times x minus y, and you've seen this before, this is from homework 1, this is a Lipschitz condition. So G satisfies a Lipschitz condition on all of AB, so for any xy in AB, and we need something more. The Lipschitz constant, capital L, has to be strictly between 0 and 1. Then we get the following. Because we already know from our earlier assumptions, Brouwer's fixed point theorem, that a fixed point exists in AB. But now we know that G has a unique fixed point, x star, and what's more, fixed point iteration is guaranteed to converge to x star for any choice of our initial guess x naught, as long as we choose it, at least if we choose it in AB. That's sufficient, it's not necessary. So we have an interval that works in terms of ensuring the existence of a fixed point. If it's Lipschitz continuous with this Lipschitz constant less than 1, then we just go ahead and try fixed point iteration, choose our initial guess however we like in the interval, and it'll converge to be one and only fixed point. Okay. And now with L having to be less than 1, the smaller L is, the more rapidly it's going to converge. We'll talk more about this later, but that's what we need to ensure a rapid convergence. In fact, if L is less than 1 but greater than a half, then you can just as easily use bisection, because at least bisection, you're going to get a 1/2 as your asymptotic error constant. And that's really what your asymptotic error constant is this constant L. Okay, and I'll talk more about order of convergence momentarily, but at least this is one condition that assures convergence. Okay. Now, notice this contraction mapping theorem doesn't say anything about the derivative of G. So G does not have to have a derivative that exists on AB. But if it does exist, then we have an alternative condition that might actually be easier to check. In fact, I'll discuss it right here, equivalence between Lipschitz condition and derivative. If G is differentiable, so if derivative exists, at least the open interval AB, then we have g of x minus g of y over x minus y, and I'm going to assume here x is not equal to y. Well, that is equal to g prime of z, where z is between x and y, by the mean value theorem. But this whole thing, the absolute value of this, I'll put absolute values around everything, this is less than or equal to L, your Lipschitz constant. So that means that the derivative is less than or equal to L, and this is true on all of AB. So that's why you can think of the Lipschitz constant in the case where a derivative exists. The Lipschitz constant is essentially an upper bound on the derivative, on the interval of consideration. And it's this equivalence between the two that leads us to the second condition for uniqueness and convergence of fixed point iteration. So what we have here is, now, actually this fixed point theorem likely should have a name, like Brouwer does. I just didn't see it in the source that I was using. So this is often referred to as simply the fixed point theorem, even though it's not very descriptive. So we're still making the same assumptions. G is continuous on AB, and G maps AB into itself. So Brouwer fixed point theorem is satisfied. A fixed point exists. So in addition to that, G is differentiable on the interval AB, and the absolute value of G prime is less than or equal to some constant L, where L is less than 1. And you can think of L as being a Lipschitz constant. It would actually work as 1. So it really is the same thing. Then you get the same benefits as in the contraction mapping theorem. And it says that if, so what happens is, as before, G has a unique fixed point, x star, and fixed point iteration converges to x star for any initial guess x naught in AB. Okay. All right. So what I should mention is, in either case, if G satisfies the Lipschitz condition, or if G's derivative is small enough, which means it still satisfies the Lipschitz condition, then we say that G is a contraction on the interval AB. Okay, that's where the name of the contraction mapping theorem comes from. That so that's what we want. We want to rewrite our original equation f(x) equals 0 as an equation of the form x equals g of x, where g is a contraction. If we are able to do that, then we can go ahead and use fixed point iteration and solve the original equation. Okay. Now, there's a couple points I want to make before I continue. First, notice I'm requiring here that G prime absolute value has to be less than or equal to some constant L, where L is less than 1. You might think that's more complicated than I needed to state. Why couldn't I say absolute value of g prime of x is simply strictly less than 1? Okay, actually, I need to add here this needs to be true on AB. Okay. So why couldn't I have just stated that? G prime of x strictly less than 1. The reason why is that would allow g prime of x to get arbitrarily close to 1. And if that is allowed to happen, it may well be that the fixed point iteration will fail to converge. Essentially, the error is going to remain stationary from one iteration to the next. It may not necessarily go to 0. So the idea is between L and 1, if you require L to be less than 1, then you're basically ensuring some separation between g prime and 1. And as a result, since the error is multiplied by g prime from one iteration to the next, you're guaranteeing that the size of the error is going to strictly decrease from one iteration to the next. That will make sure that the error goes to 0. So that's one technical point that I wanted to make. Also, another point I wanted to make is here we're using fixed point iteration to solve a single equation of the form x equals g of x, which comes from f of x equals 0. But fixed point iteration is actually one of the most powerful devices in all of mathematics for solving all kinds of equations of great degrees of difficulty. Equations that you would have no way of being able to solve using other techniques like manipulations or factoring or whatever. In fact, in differential equations, there's a theorem for general first-order differential equations called the existence-uniqueness theorem, where you prove that under certain conditions, a first-order differential equation or system of DEs has a unique solution. And the way that's proven is using fixed-point iterations. So those of you who are in my 605 class are going to suffer through that tomorrow. But you'll recognize a lot of terms related to fixed-point iteration. So it's useful for proving that a solution exists and is unique. Also, it can be used as a practical tool to solve an equation that you wouldn't have any other way of solving, because the form of it is so simple. You just try to arrange it in the form where you can just perform a successive substitution, and if you can show that the g you come up with is a contraction, and this concept generalizes to higher spatial dimension or vector valued functions, then this is an effective way of solving the equation. Okay. Now, with regards to a derivative needing to be less than some constant that's less or equal to some constant less than 1, there's a converse of sorts to this that is worth pointing out. So you can get an idea, in some cases, as to why fixed point iteration might fail. And this actually is what caused us some trouble in the first example with g of x equal minus natural log of x. So what if a derivative is too large? So one result what we have is if x star is a fixed point, so x star is equal to g of x star, and g prime is continuous near x star, and the absolute value of g prime at the fixed point is strictly greater than 1, then this is a bit of an oversimplification. So I'll be a little bit non-rigorous here and say usually fixed point iteration will not converge to x star for any x naught. So here we have a divergence result. And I say usually because, for instance, what if you happen to choose x star as the initial guess? Then of course it converges in that case. Or it may happen, again due to luck, that you plug in some x naught into G and you get an x1, and that happens to fall exactly on the fixed point. So if it happens in a finite number of iterations like that, then yes, you can get it to converge. But if it's an actual infinite iteration, it will not converge. So actually, we'll see an example on Thursday where we have a function that has a fixed point, the derivative is greater than 1 there, and we can plug in an initial guess that's incredibly close to that fixed point, and the iterates will still run away from it. So it's kind of maddening, actually. So what happens is we say that the fixed point x star is unstable in that situation, if g prime of x star is greater than 1 absolute value. Otherwise, if the derivative is well behaved near a fixed point, or we have this Lipschitz condition satisfied, x star is, as you can imagine, stable. So we have stable and unstable fixed points. It just depends on how the function is behaving. Is a derivative small near a fixed point? Or is it satisfying a Lipschitz condition with a Lipschitz constant less than 1 near a fixed point? If so, it's stable. Otherwise, it's unstable. And that's just about whether a fixed point iteration will converge to that fixed point if you choose an initial guess that's sufficiently nearby. Okay. Now, so we've addressed the condition of existence and uniqueness and convergence, also non-convergence. The next thing we need to look at is how rapidly does fixed point iteration converge? And once we have a handle on that, is there some way we can choose G to ensure rapid convergence? All right, just because I'm paranoid, I'm going to stop recording again and make sure everything is hunky-dory. Okay, good. I have 48 minutes of usable footage. Still a bit of a ways to go. So actually, this is going to turn out to be somewhat longer than class was. Sorry, not sorry. Okay. So now we're going to look at if fixed point iteration converges, how rapid is this convergence? And we can best answer that question by using our old friend, Taylor expansion. So as before, I'll let ek be the error after k iterations, xk minus x star. Now we did this expansion before for mean value theorem, but now we're going to take it a little bit further using Taylor's theorem. So ek plus 1 is xk plus 1 minus x star, but xk plus 1 is g of xk, and x star is g of x star because it is a fixed point. And now what we'll do is we'll take g of xk and perform a Taylor expansion around the center x star. So what happens is g of xk is equal to g of x star, which cancels with this, plus g prime at x star, xk minus x star, plus next term 1/2 g double prime at x star, xk minus x star squared, and so on. And I'll abbreviate this now. This is g prime of x star ek plus 1/2 g double prime x star ek squared plus additional terms, which I'll label as big O of ek cubed, so proportional to the error cubed. And we won't bother with those terms. So this gives us an idea about the order of convergence and also the asymptotic error constant. So we can say the following. First, if g prime at x star is non-zero, then we get linear convergence and the asymptotic error constant, which I defined last week for the order of convergence, so that I referred to it as C before, that is equal to absolute value of g prime at x star. Okay, and this has to be, remember, linear convergence, the C has to be less than 1, but that's what we're assuming here when we actually have convergence to a unique fixed point. So that's what normally happens with fixed point iteration, linear convergence, and preferably we should have this error constant C less than 1/2, so that it's a viable alternative to bisection. Okay, so now what happens if the first derivative is 0, so g prime at x star is 0, but the second derivative is non-zero. So what happens in that case is quadratic convergence. So it converges much more rapidly, like the number of correct decimal places roughly doubles from iteration to iteration. And our asymptotic error constant C is 1/2 g double prime of x star, take the absolute value. Okay. And if this derivative, second derivative, is also 0, then we have cubic convergence. So however many derivatives are equal to 0 at the fixed point determines, and how many leading derivatives, that determines the order of convergence. And then it also gives you the asymptotic error constant. Generally, it's going to be linear quadratic. It's not likely, except for a very fortuitous choice of g, that you're going to see anything better than that. Okay. Now, so the last topic is how do we then choose g to accelerate the convergence as much as we can. If it's going to be linear convergence, we'd like the c to be as small as possible. We would love for g prime to be 0, because then we can get quadratic convergence. So let's see what we can do. So this investigation, this is about relaxation. And what I mean by relaxation is I'm going to let g of x equal x minus some constant lambda times f of x. So this is our phi of x from before, which we wanted to be non-zero. So we're just going to make it easy on ourselves and choose phi of x to be some non-zero constant lambda. This is what relaxation is called. And the idea is we want to choose our constant lambda to for maximum advantage, to try to make convergence as rapid as possible. Okay. Now, so what we're going to do is we're going to assume that our function f is continuously differentiable. So the f prime is continuous. At least near x star, the root of f. Okay. And then we're also going to assume that f prime at the root is equal to some value alpha which is strictly positive. And that's a reasonable assumption. Because we want it to be non-zero, so it's not a double root. And if it were negative, we'll just work with minus f. Okay, so because f prime is continuous, and it's positive at this point, that means if we are sufficiently close to that point, f prime still has to be positive nearby. It can't just spontaneously dip to negative arbitrarily close to x star, because that would violate continuity. So because it's continuous, we can say that f prime is positive on an interval that is centered at x star and has some radius delta. So in this interval, x star minus delta, x star plus delta, f prime is positive. Now, this interval, as you can see from the square brackets, it is a closed interval. So we can say this is a closed and bounded set because it is a finite interval. Now there's a term for this. Those of you who are taking real analysis, this term's going to come up, so you should know it. I'm sure Dr. Ding will cover it at some point, but I'll give you a preview. This is called compact. So a set that is closed and bounded is also called compact. And the reason why that's important to us here is, okay, let's make this point out to the side. A continuous function on a compact set, such as this one, but even in higher dimensions, is guaranteed to have a maximum and a minimum. Here we have this closed interval. F prime is assumed to be continuous on it. So we can say that f prime of x is has a minimum little m and a maximum big M on this interval. X star minus delta, x star plus delta. And we're assuming that f prime is positive on the entire interval, so we can say that little m and big M are both strictly positive. Okay. Now, as a result of this, if we now look at g prime of x, so we go up here, what is g prime? Well, g prime is 1 minus lambda f prime of x. And because f prime is between little m and big M, we can say that g prime, so that's what this is bounded below by 1 minus lambda capital M, because we're subtracting off more here. And it's bounded above by 1 minus lambda little m, because here we're subtracting off as little as possible. So now we have these bounds. And we want g prime to be as small as possible. So what we'd like to do is try to make these as small as possible. And the best way we can do that is, so we want them, these combined to some interval minus k to k. So we'd like to say this is minus k, and this is plus k. And if we can make sure that g prime is centered between these two, sandwich interval minus k to k, so we have a symmetric interval, that's how we can make sure that the value of k is as small as possible, because this interval, 1 minus lambda m to 1 big M to 1 minus lambda little m, but the width of that is going to be from, so it's going to, the width is going to be from, lambda times big M minus little m. So it's going to be scaled by lambda. But if we choose lambda improperly, we might have this value too large. Or maybe this value is too large in the negative direction. So by making it symmetric, around the origin, from minus k to k, we can make both of these values as small an absolute value as we can. So here's what we'll do. We have 1 minus lambda big M is equal to minus k, 1 minus lambda little m is equal to plus k, and then what we'll do is we're going to add these two equations. So we get 2 minus lambda little m plus big M is 0. So that gives away what lambda is. Lambda is equal to 2 over little m plus big M. And if we go ahead and take this value for lambda and plug it in here, I won't work through the algebra. You guys ought to be able to handle that. This is a 400 level math class. We can actually get an expression for k. It's big M minus little m over big M plus little m. And since little m and big M are both positive, and big M is the larger of the two, then this whole fraction is positive, so it's greater than 0. And you can see that the numerator is going to be less than the denominator, so it's also less than 1. So, so this is, so G prime is less than or equal to k, which is less than 1 on this interval. X star minus delta, X star plus delta. Okay, so we've now ensured that the derivative is, as long as we pick a small enough interval where f prime is guaranteed to be positive, we're able to choose a lambda, this value of lambda, that will guarantee that the derivative is going to be small enough. Now, what we still need to make sure of, though, we need to make sure that a fixed point is going to actually exist on this interval. Without that, we can't really do anything else. So let's go ahead and take care of that. We are getting close to the end, I swear. Okay, so now what we'll do is, let's assume that x minus x star is less than or equal to delta. So this is another way of saying that x is within the interval x star minus delta, x star plus delta. Now because basically x is distance delta away from the center of the interval, which is x star. So now let's take a look at g of x minus x star in absolute value. So, well, that's the same as g of x minus g of x star, because x star is a fixed point. This is equal to absolute value of g prime of some unknown point, which I'll call c, times x minus x star. But this part is less than or equal to delta. This part is less than or equal to k less than 1. So as a result, this whole expression is less than delta. So that means that g of x is also in the interval x star minus delta, x star plus delta. So g, with this choice of lambda, actually maps this interval x star minus delta, x star plus delta into itself, guaranteeing that the Brouwer's 6-point theorem applies. And so now we have all the conditions for the fixed point theorem. The second one that I stated, the fixed point theorem applies. It satisfies all the conditions. So now we can choose any x naught in this interval, x star plus or minus delta, and fixed point iteration will converge because this particular G has a fixed point that exists in this interval, and it is a contraction on that interval. Okay. So what happens here is convergence is linear, and our asymptotic error constant C is actually K, which is, okay. Well, we have a value for K, that's big M minus little m over big M plus little m. And this is known to be less than 1. But of course, we'd like it for it to be as small as possible. Now, okay. But now let's take a closer look at this value of lambda that we've chosen. Lambda is equal to 2 over big M plus little m. Alright, so lambda, if we call, is 2 over big M plus little m. So let's let delta go to 0. And what happens is lambda converges to 2 over, so the interval x star plus or minus delta is coalescing to a single point x star. So big M is the maximum, that'll converge to f prime of x star. And little m also converges to f prime at x star. So this is 2 over 2 f prime at x star is 1 over f prime at x star. So it seems like choosing lambda to be 1 over derivative might be an advantage. But let's think about this for a second, and actually, I have to confess, this is a point that I should have made when I gave this lecture earlier today, so in one sense this lecture is better, even though it's longer. But the point is also made in the notes. So if we recall, G prime of x is 1 minus lambda f prime of x. So if we go ahead and let lambda vary from iteration to iteration, let's just make it 1 over f prime at xk, then G prime at xk is equal to 1 minus 1 over f prime at xk times f prime at xk. Well, these cancel and become 1. Subtracted from 1 gives you 0. And that's the ideal situation. We would like for G prime to be 0 because that is what gives us quadratic convergence. And as we try to pick a best possible lambda to make the derivative of G as small as possible, we see that as the iteration converges, lambda appears to be approaching 1 over derivative at the fixed point anyway. So we can serve ourselves better by going ahead and using this variable lambda from iteration to iteration. And in fact, so what this means is, if we consider this using for our g of x, x minus f of x over f prime of x, which is really what is happening here by using this choice of lambda, then g prime at the root x star is, let's take a derivative, 1 minus, and here we need the quotient rule, which is f prime squared minus f double prime, and x star is plugged in throughout, all over f prime and x star squared let's simplify this. F is equal to 0 at x star. So that is gone. And what's left? 1 minus f prime squared over f prime squared. So this part simplifies to become 1, so we get 1 minus 1 is 0. So in fact, this choice of g, x minus f over f prime, gives us quadratic convergence. And this has the effect of using this ideal convergence, the ideal variable lambda that makes g prime equal to 0 at each step of the iteration in order to give us that quadratic convergence. The asymptotic error constant we'll see later because this method I described where xk plus 1 is equal to this g of xk, xk minus f of xk over f prime at xk. So this is not just any old fixed plane iteration. It is well known as Newton's method. And that's a method that will be covered next week. Now, I'll be gone next week, and when the substitute, Amber Sumner, covers Newton's method, as well as its close relative, the secant method, she will derive this method in an entirely different way that's actually more intuitive, but both points of view are quite educational. So I figured I'd do one and she'll do the other. Okay, so let me just check my notes to see if I have anything left. Nope, in fact I do not. So we're good, and so now I'll go ahead and put this on YouTube and try some enhancing, and hopefully it's something that you're able to follow, at least visually. So, okay.